All right. And to finish things up, Sasha will give you the final thought.
Great, thanks for sticking around. So let me wrap up the abstract discussion of p-adic comparison functors of this Riemann-Hilbert functor, and then I'll try to get to some applications. So finally, let me, at least at some level of detail, give you the definition of one of those functors. So we had this smooth variety over a p-adic field. And let me describe how this functor d is constructed. So it's a functor from QP local systems. To filtered vector bundles with connection. On X. So again, it's a bit of a slang. It's a vector bundle with connection, such that the underlying bundle has a filtration, which satisfies Griffith's transversality. Right? And so this was one of those functors which was not fully faithful. Which was not faithful. It was killing some objects which are non-de-Rham local systems. And then there are refinements of that, which I was calling RH+. But let me just describe how this d-de-Rham is constructed, and you could even guess what will be the construction of these refinements. It will, again, as in the case of a point, will be certain intermediate steps in the computations of d-de-Rham. So the key is really the construction of certain period rings, but really now, well, it's more interesting because we're working over some interesting base, and so my goal is not just produce a single module, but a vector bundle. And so how do we go about this? Well, it's in a way reminiscent at first to the construction of the complex Riemann-Hilbert correspondence. So I said that the key will be certain period rings, but if you remember, in all these period rings computations, it was very crucial to always work in the p-completed setting. So something interesting was happening when we were taking some p-adic limits. And now I'm trying to produce a vector bundle of connection on algebraic variety, even though the varieties of a p-adic field, say the functions on the variety is not a p-complete algebra. Which is why Ziyu introduced for us rigid-analytic geometry yesterday, and this is the framework that we'll use. So let me, for simplicity, assume that X is proper. Just how for complex Riemann-Hilbert this was a simplifying assumption, and there's interesting additional ideas needed to make it work for general X. And let me, on this token, let me introduce properly the attributions for these things. So it has a long history. I think morally this starts with Markov followings. I think in this particular case, at least locally, this was first considered by Bernon, and then really put in the present form by Scholze, Liu-Zhu, and then Diao, Lan, Liu, and Zhu. And the last of these papers is exactly generalizing this to non-proper varieties, which involves kind of a version of Schmidt's nilpotent orbit theorem. But I'll not get into that today. So I assume X is proper. So we're trying to produce a vector bundle with some additional structures. So what does it take to define a vector bundle in X? Let's even neglect the additional structure for a second. So there is an analog of a Gaga theorem in rigid-analytic geometry, which says that this is the same since X is proper as vector bundles on the rigid-analytic identification of X. But let me try to say more explicitly how you think about those objects. So you kind of give us a sketch of, give us a flavor of how to think about those things. So if you could find a cover of this space by affinoid algebras, then maybe not so surprising that you can think about vector bundles using gluing data. So it's a collection of vector bundles on these charts plus gluing data. So on the intersections there are isomorphisms such that on the triple intersections there is a cocycle condition which is satisfied. And hopefully, well, if the rigid-analytic geometry is working as we expect it is, then vector bundles on affine charts is just the same as projective modules over the ring. So it's the same as projective modules. So in other words, I've reinterpreted this category of algebraic vector bundles on X as a collection. So the data of a bundle is the collection of modules over these p-complete algebras with some isomorphisms. So ultimately also a more algebraic condition. And but this Gaga isomorphism is really a non-trivial thing, as it is in complex geometry. And let me just say explicitly what this is saying. So it's saying in a particular example. So for instance, when my variety is P1, of course local systems are not so interesting, but what's an example of this description of the category of vector bundle? So it's a choice that I make of charts, and I claim that one example of such a cover is, so in the algebraic geometry, you can cover this by 2 copies of the affine line with coordinates x and x inverse respectively. And now the analytification you can cover by the affinoid space attached to p-completed versions of the same algebras. So the Tate algebra in the variable x and the Tate algebra in the variable x inverse. Right? And Zayu told us that points of this are well, elements of your test algebra whose norm is at most 1, and points of this are right, and the same for x inverse. And now, well, whenever you have any point on P1, if you write it in homogeneous coordinates, the ratio taken, it will be point of homogeneous coordinates A, B. And of course, either A over B or B over A has a norm which is less or equal to 1, so it will make it into one of those charts. And so, in other words, vector bundles on P1 are the same as pairs of modules over these rings, sorry, projective modules over these rings, with an isomorphism over this Tate algebra where I join both x and x inverse. Okay? And the claim is that it's equivalent to the category of algebraic vector bundles on P1. So now, if I have a local system and I'm trying to produce this functor d de Rham, the value of this functor d de Rham of L, all I need is to supply the values of the restriction of this vector bundle on these charts, and then the gluing data. So suppose L is a local system. And so let's say that R was one of those charts. So I can restrict it to SPR. And this is again an object which you can think of in purely algebraic terms. It's the same as representation of the Ital fundamental group, but just of the ring R thought of as an abstract algebra. So in the original geometry, the definition of Ital covers of these affinoid rings is just the usual algebraic notion. So now given such a thing, I'm trying to produce a projective module over R. And so the description will be very similar to what we saw over a point. It will be this period ring construction. And of course, the key is to define the relevant period ring. So, kind of as we saw over a point, over just the case of K, the key building block for all these period ring constructions is to pass from the original ring you were working over. So previously it was this K, now it's a more complicated algebra R. So you pass to there it was an algebraic closure, and then you complete. And here, well, let me pass to its integral closure. So let's say I'll assume that R is a domain, and then with integral closure in the field of fractions. And I can further p-adically complete it. And the key claim is that there is a certain construction which you can attach, well, say, to any p-adically complete algebra, which I'll call OB the rem. It depends on R hat bar. And right, so let me just say in words that this takes as an input any algebra living over R. So it depends on the base of R. And so this is something which by functionality has an action of the étale fundamental group of R. And the construction is that I should take this transitor from my local system and take invariance. Okay. So of course the question is, what is this period ring? So let me not give you a full definition of it. There is an extremely clean way of doing this. Let me rather give you a less clean special case description of it, but which will hopefully sound somewhat motivated. But before I go there, are there any questions about it?
I'm sorry, what was R bar and group closure and outbreak closure fraction?
Yeah, exactly. Sorry, maybe I misspoke and said it. Yeah, so let's say in frac R. But great. So I organize all finite étale covers of all connected finite étale covers of R into a direct system and take a column.
So why? Sorry, it's only, but so is that really the integral closure?
Oh, I'm sorry. Sorry. Let me.
Right there.
Sorry.
Oh, right there.
She said it. Sorry. Sorry, this was the terrible terminology. This is, I was trying. This is supposed to be a limit of all étale covers. So
the universe.
I'm sorry. Yeah. So I organize. Yeah, thank you. Great. Yeah, thank you very much. Okay. So it's something which fundamental group acts. Right. So the question is what this ring is, so what do we expect from it? Well, we expect. I said that one of the desiderata about this theorem of L is that it's a bundle whose stalks are at various points are the results of applying Fontaine's function theorem to various stalks of the local system. So, so in particular, it means that elements of this ring, it should be some gadgets which can specialize into elements of the usual theorem well attached to a discretely valued field if for various points of the base. So it should be some family version of that. And let me not say explicitly what the definition of that is, but let me rather say that this has as the original theorem, this has a filtration. So with which is still z indexed as before, with associated graded, so I graded pieces being certain sheaf, which is now a version of what we were previously calling C, and with all the tape twist. So here, well, this is still just the cyclotomic character of the Galois group, and well, by one étale of this R, since R lives over K, it maps to the Galois group, right? So OC is a certain gadget with action of the Galois group, so it's a slightly non-traditional notation, and I'm not sure it's the best one. But so let me say what these OCs were. So let me remind you that that when R was just K itself, then R bar hat was this complete algebraically closed field C, and then in this case OC is just C itself, right? So there's nothing fancy happening. So maybe I should say OC of C. But now when we're in this geometric situation, we actually will want more. We don't want OC to just be R bar hat. And let me indicate why do we want more. So again, what's the kind of goal in constructing all these period rings? So we definitely want this functor to behave reasonably to output the bundles of the right rank on L which were of geometric origin. And it's not obvious, but it can be checked that if I simply, so kind of first guess, is that OC of this, in the geometric case, should be just this completed algebraic closure. But this is too small, because it turns out that it doesn't contain periods of some local system, local systems which you definitely want to see there. And here's this one class of such local systems. So example, it's called Kummer local systems. Okay, and in this particular case, for this discussion, let me already specialize to a particular choice of R. So let me assume that my R was one of those Tate algebras that you introduced. So it's let's say we work with d-dimensional varieties, and so this will be a p-completed algebra generated by d variables, which are inverted in a p-complete sense. And so as an algebraic geometry, if you have any smooth, so in algebraic geometry, if you have any smooth variety, then locally there is an Intel map to the affine space, or you can always shrink further. There will be an Intel map to some power of GM, and a p-adic analog of the statement that locally there is always an Intel map to such an algebra. Let me just assume that R is this algebra itself. You might object that in algebraic geometry, a power of GM has a very boring fundamental group, so maybe I'm cheating here slightly. But first of all, I claim that the construction will work immediately similar for R, which are retail over the string. And also another point is that Ziyu showed us that actually already this algebra has many more interesting finite covers than its algebraic cover. So this is not too bad of an omission. So you have this R. And now, what is a local system whose periods we're missing so far? So in general, if you have any algebra, let me contemplate what are the local systems which are extensions of QP, the constant local system by QP of 1. Okay. So these are classified by the first X group of the fundamental group from QP to QP of 1, which is nothing other than first the homology of this rank R with coefficients in QP of 1. But now, one way of producing elements in this is by the Kummer theory. So if you run the Kummer sequence, then there'll be a natural map from the units in your algebra R into here. And if you have an element here, then the extension which you get, it's basically the Galler representation. Abstractions to splitting this extension is finding a compatible system of p power roots of your element you started with. Right? So let me take one of those coordinates which I have, and let me produce the associated Kummer local system. So if I call this map kappa, then it's a local system such that its class in the X group is the image of xi under kappa. Okay. Now this local. Was there a question?
Is L like QB?
Say again?
Is L less QB like the locus?
Right. So this is a QP local system on space spectrum of R. Or any variant. Right. Now I claim that well, okay, maybe we only talked about well, it makes sense here as well. I claim that these LIs are all of geometric origin. So remark that LIs are of geometric origin. So technically, whenever we spoke about local systems of geometric origin so far, they're always semi-simple, and we were always finding them in cohomology of families of smooth proper varieties. So this is, of course, the interesting data here is that this non-split extension, and so this Li can be exhibited as the first cohomology of a family of non-smooth and non-proper varieties. It's a pleasant computation to come up with such a thing. But in any case, we certainly want my functor d de Rham to output a rank 2 bundle on these local systems Li. And it turns out that to get the correct object OC from this naive guess, we should simply adjoin p-adic periods of these local systems, and then we'll be done. So the correct answer is that OC, oops, this case, is I should take this first guess which was correct in the case of a point. And then I should just adjoin in a non-completed way several elements, and I'll define the action of the my fundamental group on them in the following way. So, where action of phi 1 is defined so that these VIs can serve as p-adic periods of my local system. So in other words, if I were to choose, so my local system Li, it was an extension of Kp by Kp of 1. And again, maybe if I choose a base point, then I'm thinking of this just as a two-dimensional Kp vector space with an action of the fundamental group. So let me choose a basis here, such that E0 maps to a basis element here, and E1 spans a subspace here. And then, well, the choice of this basis depends on the choice of some roots of my xi's in this algebraic closure, but let me make this choice. And so the I is defined so that if I take the element, so the action of the Galois group, of the fundamental group on VI is defined so that if I take inside OC of R at the bar, I take an element, so I want to find here an element which will be invariant by the fundamental group. So it will witness the fact that my d-ram is not too small. And this element should be E1 tensor this VI plus E0 simply tensor 2. So that this element belongs to the invariant independent. Right, so I said it in some slightly indirect way. You can unpack this very easily into saying what the action of VI should be. But let me just say this in this seemingly more cumbersome way because it motivates why this VI wants to be there. Right. And so I claim that this uniquely pins down how the Galois group, how the fundamental group acts here. And then my claim is that these gadgets can be glued in an interesting way into this whole beta-rum, such that this filtration exists. And maybe more importantly is that actually all these choices of coordinates, they were unnecessary, and there was a canonical way of coming up with beta-rum. But since we're trying to get some motivated introduction into p-adic Hodge theory, I think this is one of the motivations that you might want to look at these things. And now the miracle is that I don't have to adjoin anything more. So now, having performed this construction, I already got all p-adic periods of all local systems of geometric order. And this miracle, you can think of it as a kind of its mechanism behind it is the same as the almost purity theorem, which we saw 2 days ago. So if you like, morally, when you started with C and you've gotten to beta-rum, you've basically adjoined in some interesting way an element T, which was a period of this economic character. And here it turns out that you, to this completed algebraic closure, you don't only adjoin periods of this economic character, but also periods of all these Kummer systems, all these Kummer local systems. And this turns out to be that. So this is, of course, only the beginning of the story, but this turns out to be the shape of these periods. And then, if you trust me that this construction can be made functorial and dependent of coordinates, it's not surprising that this glues well into analytic bundle, which then magically algebraizes by God. And I only talked about vector bundles so far, but somehow, as we saw over a point, the additional structure on d-rum was coming from an additional structure on this period ring. And the same happens here, is that this OB-rum comes with a flat connection. And there's a filtration on OB-rum. And both these structures are compatible with the action of the fundamental group. And therefore they induce for me something on these invariants.
I have a question. So you said this L is you interpret it as a triple local system on spec R.
Yeah.
But like originally it was just on the X. I mean spec R is like something more like analytic than originally.
Yes, that's right. Yeah.
So you just take pullback?
Oh, right. Sorry, I was just. This was kind of a general discussion that. I mean, probably the correct discussion of these period rings, it should be intrinsic to R. Right? If I'm claiming it's going to be functorial, there should be some procedure which starts from R.
I see.
Right. I mean, if you feel more comfortable, you might as well. Sorry, you might as well have worked over algebraic GM to the power D, and there is an analogously defined common local system. You can then restrict it to this thing.
I see.
We'll still be no split there. So this is my spiel about definition of relative p-adic Hodge theory, and now I'll try to move to something which I'll try to make very resemblant to Hodge theory, which appeared in anti-stock. Then we'll try to connect it to some of the conjectures that Daniel and I spoke about a little bit. But before I move there, are there any questions?
Sorry, I didn't completely follow about it. Why did you make it so that that particular class isn't?
Oh, well, so my goal was to just ensure that this is non-zero to begin with. So I want some invariance at least.
Okay.
And I'm just saying that if my local system was just QP, then it does have its own period. Its period is just 1, right? Because already the action theory is trivial. So now, probably if I'm trying to come up with a period for Li, it should be a lift of this period in QP. So it should better map to E0 tensor 1 under this connection.
One more question is like, why do you just algebraically adjoin these if you want to reveal it? Don't you want something like p-adically?
Yes, this is a very good point, and it's not immediately right. It's the reason is that basically all the actual local systems which you'll encounter in this arithmetic setting. So suppose I only so let me say it this way. All the other periods which you would have wanted everything that you would have wanted to achieve by p-adically completing this is already achieved by taking linear combinations of elements in this p-completed algebra. And this has to do with the fact that, for instance, if you took, as in Glebstock, if you took a particular intermediate cover of this guy, which was kind of the result of adjoining all roots of unity to k and all p power roots to x. Then, so I can consider this cover. Its Galois group is this gamma k, which is just a cyclotomic Galois group, and then some direct product with several copies of ZP, so it's this Kummer extension. Then whenever you have an action, suppose you only look at local system which factor through this quotient. Then there, the monodromy operators sitting in ZP of one in this geometric part of this Galois group, they'll always act quasi-unipotently by what Lebesgue split. And because of that, the periods which you need to encounter for them will be polynomials in these VIs rather than power series.
Maybe just one last thing. Sure. I guess if you take a Riemann invariant of this OCR, do you get just R back?
So, I think for a second. Yeah, right. It's the case of computing. Right. It's the case of computing this functor on the trivial local system, and that's what we want to get there. Right? We want to get trivial rank 1, 1. Right. All right. Let me now connect this back to what I was trying to talk about in the first on the first day. So we saw this conjecture. So now we're moving away from the p-adic world, but we'll go back into it for all actual proofs. But the statement will not be p-adic anymore. So we were working with varieties even over complex numbers because there was some smooth variety, and we had this conjecture that if you have so for a semi-simple PP bar local system, L on S, again just a topological notion so far, L is arithmetic, so extends to a spreading out of S to some finitely generated field, if and only if it was a geometric origin. And I think, as kind of Daniel, for instance, emphasized, this is if we're going to trust this that this arithmeticity condition is sufficient to get that your local system came from homology of varieties, we should better be able to somehow recover directly the variation of Hodge structures which would come from this geometry. And so far, I think it's a very interesting problem to do that. I don't think we're in any way close, but I claim that using using p-adic Hodge theory, you can at least try to make the first step. So this functor d-rum, it's a way of producing, starting with a local system and producing something which looks a little bit like a variation of Hodge structures. At least there's a vector bundle with connection, and there's a Hodge filtration. There is in no way of polarization so far, which is really the crucial piece of data. But we have to start somewhere. But as I emphasized, there was this issue that the d-rum, it was killing a lot of objects. There are many non-drum local systems. And so if I know that my local system is arithmetic, then I know that there exists some local system L tilde on some spreading out of my variety over some finally generated subfield of C. So now we're at least in a position to run p-adic Hodge theory on it, because we could we could embed we could embed F into some finite extension of QP and get a p-adic local system out of it. But no one guarantees to us that this local system would run to begin with, and in general it won't be. But it turns out that the following is true. So let me first of all, before stating a purely p-adic result, let's kind of contemplate this arithmeticity condition. So you might be slightly suspicious of it because it's saying that some structure exists, but it doesn't seem to, at least in this conjecture, the specific choice of the structure doesn't seem to enter. But I'm saying that it's not too bad of an omission. So for instance, so a remark is that if L was not only semi-simple but irreducible, then if you found any other extension of L to a local system over this as 0, then for any other, let's call it L tilde prime on as 0 over F, which restricts to the same local system L, or if you go to topological local systems, which is just to say that L tilde restrict to the algebraic closure was isomorphic to L tilde prime. Then this other local system just differs from this lift which I already had by a character of the Gell. And this is in complete parallel with the result which Andy explained, that if you had an irreducible local system, then any two, if there was at least one structure of a complex variation of Hodge structures in it, then any other one would be a twist of the first one. And somehow, Andy really had to prove, non-trivial theorems to prove such a statement, this theorem of the fixed part. And remarkably, in the arithmetic, this is a much softer statement. It basically follows, let me not write it down on the board for the sake of for the sake of time, but it follows immediately from considering as Andy did, the local system of homomorphisms between L tilde and L tilde prime, and using that on a space of global sections, there's a natural Galois action. And so sort of this phenomenon that some of these statements from Hodge theory become easier in arithmetic will kind of appear over and over, because in a way, when you're working with arithmetic local systems, there is already a built-in action of the Galois group, and all the operations which you can think of are immediately compatible with it. Whereas when you build the theory of operations of Hodge structures, whenever you do some operation on local systems, you have to explain why this operation is compatible with why this operation can be enhanced to an operation in the category of operations of Hodge structures. And often this requires non-trivial theorems. And in fact, as a historical aside, my understanding is that for Deligne, the motivation to introduce the variations of Hodge, he was not the first one to do it, but the motivation to think about the variations of Hodge structures the way he was doing was coming from contemplating local systems over varieties over finite fields, where again this Galois action is some feature which is built into the story. And we'll hopefully see a manifestation of that just now. Okay, so the upshot is that of this remark is that this extension is essentially unique. Okay? So notice it's a really, if you peer into this, it's a really remarkable statement because we started with a single representation of its topological fundamental group. So it was, as Daniel says, just a bunch of matrices for generators, some relations. But now if this arithmetic extension exists, then it means that in particular for every rational point of this spreading out, we've got a Galois representation. And so all this huge collection of Galois representations is remembered by the original topological monodromy, well, up to this twist by a character. So now, okay, we've got this spreading out. Now, it turns out that the following is true. So let me shift to a slightly different setting where the statement, I want to emphasize that the statement is really purely p-adic. So let me go back into a setting where I have a smooth variety over some p-adic field. Then it turns out that, maybe I should emphasize that none of what I talked about so far was original work. It was my attempt at exposition at the work part of it. So if L is a QP bar local system on X, so now that I've slightly changed the notation here. Now I want my central object to be a local system on a variety over a non-algebraically closed field. So this is, when we try to apply this, this will rather be a restriction of L tilde, but let me just stick to this notation L. I hope it's not confusing. Let's assume that this restriction to the geometric fundamental group is irreducible. Then you can find the character of the Galois group of this p-adic field such that if you twist my local system by this character, and I invite you to think about this as just coming up with a different way of extending this geometric local system to a local system on X, such that that new local system is the Rho. So technically speaking, it's a QP bar local system now, and I only spoke about notion of drumness for QP local systems, but this is not really an interesting distinction because in fact any QP bar local system is automatically defined. Its coefficients can be descended to a finite extension of QP, and then the notion of drumness for it, it just means that so it's a local system of E vector spaces where E is some finite extension of QP. Let's just forget the E structure and view this as a local system of QP vector spaces of a larger range. And the notion of drumness just means that this underlying larger QP local system is the Rho. Okay. And we can immediately kind of restrict to the case of, if we like for exposition at least, we can restrict to the case when L had a QP structure, right? So in particular, this means that, so if L is the Rho, so if you've managed to twist the local system by a character to make it drum, then you can make the associated bundle. So it's a vector bundle with blood connection of the correct ring. And filtration. But now I'm saying that this L, this new vector bundle, it looks resemblant of a variation of Hodge structures, at least there is a filtration. And you can prove certain semi-stability statements about the associated Higgs bundle. But remember that if we're trying to test this conjecture, if we start with an arithmetic local system, there was this extension. So we're trying to equip this original local system with a variation of Hodge structures. And so in order for this output to be helpful for this, we need to have some compatibility between complex Riemann-Hilbert correspondence and p-adic Riemann-Hilbert correspondence. So let me phrase this as a question. I think maybe in a slightly different shape, it's been raised by Diao, Lan, Liu, and Zhu, who in some cases answered it positively. So I have a p-adic local system here. So this is the Rhom local system of X. So let me choose an embedding of my field K, let's assume it was a finite extension of QP, so such an embedding exists for cardinality reasons, into complex numbers. Then I could ask, is there any relation between base changing my vector bundle of flat connection onto from K to complex numbers? So now it's a vector bundle of flat connection on a complex variety. And now by complex Riemann-Hilbert, those correspond to just topological local systems of C vector spaces. So in other words, if I just consider the associated analytic bundle, and if I consider the local system of flat sections, this is some C local system. Is this related to the C local system which you get out of L? So you could have restricted L to its base change to you could have restricted L to the base change of your variety to the complex numbers. Now it's a QP local system on this complex manifold, but I could extend scalars to complex numbers because QP was a subgroup of K in particular, so it could embed it into complex numbers. And so this is asking whether this p-adic Riemann-Hilbert functor was compatible with the complex Riemann-Hilbert functor. Right, so what I did here, I started with p-adic local system, applied the p-adic functor, and then I applied the inverse of the complex Riemann-Hilbert functor. And I'm asking whether I've got the original local system. To even ask this question, I have to somehow link p-adic and complex coefficients. I've made this choice. So if we could answer this question, then this would be really an indication that my original arithmetic local system had a variation of Hodge structures, because this bundle has a filtration, and so this gives me a part of the package of data for equipping this complex local system with a CVHS. But as I hopefully convinced you, the formation of this vector bundle was very complicated and was purely p-adic, doing some p-adic periods, whereas here we're taking flat sections for some complex holomorphic connections. And right, so this question does have a positive answer. If my L was the whole local system of homology of a family of varieties, but there's some partial results, but in general I think it's wide open. And I'm not even sure if you're supposed to expect it in such a generality where you start with an arbitrary p-adic local system. I want to emphasize that this is a key question. Great. Are there any questions about what I said?
That was a QP bar local system and your answer was QP.
Right, sorry. So, let me, thank you. Let's say L was a QP local system. If I started with QP bar local system, then d diagram of L would not simply be a vector bundle on X, rather would be a collection of vector bundles on base changes to X, of X to QP bar along all embeddings of K into QP bar. So, I could have stated this for a QP local system, but it's just that the condition that I really want, so let me actually, when I'll be proving the theorem, I'll immediately reduce to the case of QP local system, and I'll be clear what I'm going to say. Imagine that someone gave you a QP local system. Yeah, thank you, you're right. What I said was very confusing. Other questions? Oh, Eddie.
So in this situation, where it's true,
Yeah.
embedding on both sides is the same.
Yes, crucially, yes. I think only in that case it will be true. I think if you trace through complex comparison theorem and p-adic comparison theorem, that's what you would get. Okay. So let me try in the remaining a little bit less than 15 minutes explain where this drums come from. So if I had a QP local system p-adic variety X, then so we're trying to evaluate this functor d-determinant, but yesterday I said that there are refinements of this functor which was going h and rh plus. So let me remind you how they look like. So two Higgs bundles on this xk infinity. So my notation for this was m. So Higgs bundle means that there is a Higgs field. And there was also an additional operation induced from the action of the Gabler group, which was interacting with the Higgs field non-trivial. Okay, and there was also a functor RH plus two vector bundles on this tube around my variety, which, well, I had two different ways of packaging the same information, but let me here write it as the data of a connection in the geometric direction, as I was calling it, which was allowed to have poles, logarithmic poles along t, sorry, not logarithmic, but simple poles along t, that I should call it. But this is only encoding derivations along the vector fields on X. And then there was this additional operator, which was commuting with connection. But the operator was not quite, it was xk infinity linear, but it was not linear with respect to the multiplication by t. So rather, it satisfied the semi-linearity condition that there is a correction term, which is the action of this Euler vector field. Okay. So there were these structures, and their relevance for us was that they help detect they help detect whether a given local system was de Rham or. So L is de Rham. If and only if I took this bundle RH plus, and if I inverted T, so that now I allow arbitrary poles, if you like, and so now I get a genuine connection here. So if the action of phi on this module was trivial, which is to say that the kernel of phi, phi was this funny this kind of object which behaved as a T connection. So kernel of phi would now be naturally an OXK infinity module. And so the rank should be as large as possible. So it's equivalent to saying that if I'll divide phi by t and I'll be thinking about it as a genuine connection, that somehow the connection in this arithmetic direction t has enough flat sections on this puncture disk. So where does this come from? So I made the I mentioned the slogan before that thanks to these functors h and rh plus, you could think of arbitrary local systems which are not necessarily de Rham as resembling variations of Hodge structures, but where the weights are not just integers, but rather elements of k-bar. Now let me try to clarify what I meant by this. So it's a crucial derivation made by Shimizu. And he did he did kind of the key foundational work to define these deconvoluted versions of these functors. Is that if I consider this phi acting on h, yeah, maybe I should have reminded you that this h is recovered from RH plus, just as it's not T reduction. If I look at, this is the question which Daniel asked at the end of yesterday, let me just put it on the board explicitly, is that this is a Higgs bundle equipped with an endomorphism. And in fact, it turns out that the characteristic polynomial of this endomorphism its coefficients are constant across my variety. So if t is my formal variable, then a priori it's an endomorphism of a vector bundle. So its characteristic polynomial, it's a polynomial in the variable t, whose coefficients are global functions. But my claim is that its coefficients are actually constants. Okay. And so, well, this would be clear if my variety was proper, because then there only, if my variety is connected and proper, then the only global functions are constants, but it's actually true even for non-proper varieties. And this, let me not go into details of that, but it's not a formal consequence of the structure H. It uses the fact that this H lifts to an RH plus. And ultimately, this comes down to the fact that this phi commutes with a connection, and you can prove that these coefficients of the characteristic polynomial are actually flat for the differential on functions, so they're killed by the differential.
So I guess by constant you mean k if you.
Yeah, so in fact, right. Great. So in fact, you can prove that they actually lie in k of t. Yeah, thank you. I wanted to blur this difference. This regards an additional argument, and this comes from the fact that secretly there was a residual Galois action here, which this phi was commuting with this Galois action. So this will not be so original, right? And now, so it means that if I have a vector bundle with an endomorphism with constant multi-set of eigenvalues across the variety. So I can decompose it as a direct sum of generalized eigenspaces, where lambda now runs over all arbitrary envelopes of k bar, where this is the direct sum and where phi minus lambda is no body. And now by this relation between the Higgs field and the operator phi, the Higgs field interacts in an understandable way with this decomposition, right? Because where can it take a subspace where phi minus lambda is nilpotent? It should take it to a subspace where phi minus lambda minus 1 is nilpotent. Because only in this case would this condition be satisfied. So now you see it's kind of, it's very reminiscent of a notion of a system of Hodge bundles or Higgs bundles attached to a variation of Hodge structures. Except that for a complex geometry, there would have been, these would have been labeled by integers. Now they're labeled by p-adic numbers. Okay? So now in the remaining 5 minutes, we started at noon, right? Yeah. Or we should finish it like 1 anyway. Great, good.
Just to clarify, should I think about this lambda as a Hodge state number?
Exactly. That's exactly right. Okay, thank you. Exactly. My definition of, sorry, not Hodge state numbers, but Hodge state weights.
Weights, right.
So they're, if you're in geometric setting, they're always integers. The multiplicity of the weight to remember is the Hodge factors. So if this condition is satisfied that your local system, that this phi had enough, the kernel of this phi was large enough, it's in particular it's true that if I look at phi acting on h of L, so on the mod T reduction of this lattice, then this is semi-simple and has eigenvalues which are integers. Right, because this is saying that this vector bundle with a connection on a punctured tube around my x, it was trivial in the direction of the t coordinate. So in particular, if I choose any lattice there, then the residues of the connection will have to be integers. So this is not quite a necessary and sufficient condition. Even if this was true, there is still an additional property. And if you thought about the p-adic Hodge theory, then this condition, which I stated, is what's called the Hodge state condition. But in the interest of time, let me just demonstrate why, by twisting an irreducible local system by a character, you can always achieve that condition. Okay. So there was a lot of there was critique of this Riemann-Hilbert functor for it not being fully faithful and not being an equivalence. But in fact, the situation is not too bad. because actually you can you can extract from it a clean statement about a clean fully faithfulness statement. So let me, for simplicity, assume that now my variety was proper. There is a natural version of this for open varieties as well. So then I said that this functor h or rh plus, there are in no way, they were not fully faithful, they were killing some information. But they preserve information about the geometric monodrome. And so it's kind of similar to, well, formally similar to what appeared in Daniel's discussion of companions. And in the interest of time, let me just state a specific consequence of it. So if L1 and L2 are two local systems, then if you're computing maps between them as geometric local systems, so forgetting the action of the Galois group, then that vector space, at least if you transfer it up to C, is naturally isomorphic to Holmes between the associated Higgs bundles. So it's a maps between bundles on xk infinity, which commute with the Higgs field, but this is completely disregarding this additional operator, similar to how here I disregard the action of the Galois. And now this is a k infinity vector space, but you should transfer it up to C. And you might have guessed that this is an instance of a Hodge-Tate comparison in families, kind of for zero of cohomology of the home local system between L1 and L2. Okay? But now you see, so I'm saying that kind of non-fully faithfulness of this functor, it all has to do with the arithmetic additional data. But it preserves the geometric isomorphism class of my local system. But now, so let me say something, let me now give a partial proof of this determinist result, is that let me assume that L is a QP local system. Such that if I view it as a QP bar local system, then geometrically it's irreducible. So I wanted to go up to QP bar and really demand this absolute irreducibility condition. Because in this case, Schur's lemma tells me that all endomorphisms of my local system are scalars. So, right, they're all spanned by the identity endomorphism. Again, endomorphism of the underlying geometric local system. All right? But now let's contemplate this together with this comparison. So these geometric endomorphisms are all scalars, and the dimension of the space of endomorphisms of my L is the same as the space of endomorphisms of the associated Higgs bundle. So it should also be true that all the endomorphisms of the associated Higgs bundle are scalars. So identity times k infinity. Okay? Or else this isomorphism would fail. But now let's contrast this with the decomposition which we have here. So this decomposition, it's as written, it's not a decomposition into it's a direct sum of Higgs bundles, right? Because the Higgs field does not respect it. But you see, it only goes from elf from sum indexed by lambda to a sum indexed by lambda plus 1. So, but now these lambdas are a priori arbitrarily numbers in k bar. But now it follows that eigenvalues of phi have to belong to a single coset of k bar mod z. Right, so they all have to be integral shifts of a single element in k bar. Because if there are two eigenvalues whose difference is not an integer, it would mean that I can decompose this bundle into two direct sums according to these two different cosets, and this Higgs field is always operates within one coset. Kind of very similar to the argument that AD gave, that even if there was ever a gap between Hodge-Tate, between Hodge weights, there would have to be some vanishing statement about the Higgs. But now we're in business because, so I learned that my eigenvalues, they lie in a single coset of k bar mod z. So let me just finish it here. So this is a continuation of this proof. is that then it follows that eigenvalues of phi, they belong to a shift of some number in k-bar. And then all that remains is to find, so if you take a character chi of the Galois group, this character, it might take values in qp bar rather than qp, but we explore this detail, such that if I apply this functor h to this character, then here phi would be acting by minus a. So for instance, if a was a p-adic integer, which is close enough to 1, this chi could just be a powerless atomic character. Then for the tensor product of L with chi, the eigenvalues of phi here would be integers. Now, well, I promised to show you that actually the operator was semi-simple, and now hopefully, given the spectrum data that I gave you, now it's just linear algebra. It's a pleasant computation to prove that actually this phi has to be semi-simple, or else this Higgs bundle would have more endomorphisms than just scalars. And similarly, you can beef it up to actually prove that the phi acts trivial in this whole bundle over the Lorentz series. And so, kind of the slogan is really what appeared in Andy's talk, is that this geometric monodromy condition constrains the type of Hodge or p-adic Hodge structure which you can have on the fibers. So, sorry for going over time, looking.
When you mentioned Schmidt's result, you mentioned like some decompletion of this function.
Yeah.
Like that means like this RH plus,
Yeah.
but the t is not formal variable, it's just.
Oh, no, sorry.
Or,
I meant the versions I wrote, they're already p decompletions. I meant k infinity rather than k infinity.
Yeah. So one thing that you've done is, so for each embedding of your ground field F,
Yeah.
so for p, you get a vector bundle. This is p-adic, right?
Correct,
So you
yes.
kind of expect that bundle to descend to some finite extension of F, probably. Okay, surely it's not going to be provable, but I'm wondering if you can get it over a finite extension of F tensor Q.
Sorry, but that's kind of tautological, right? Because sorry, you're saying I have a local system over a number field F. So for every embedding of sorry.
Oh, F is some finite recurrent.
Oh, you mean as opposed? Well, let me think about it. Please.
Is it possible to explicitly find this twist which makes your inducible representation?
Yeah, kind of. I mean, it's well, this is sure, right. I mean, for instance, if again, if A was say if A was a p-adic number, again, if you convert into 1 mod p, then this should just be the A powerless economic character. There's not really a canonical choice, if you like. Maybe one way, maybe along the lines of what you're saying, you could rephrase this as saying that if you didn't modify L at all by some random character, but rather if you just chancered it with the dual of its stock at any point, so let me just tensor L with the dual of a stock at another point. So it's kind of now a local system of larger rank, but geometrically it's just it's a direct sum of a bunch of copies of L, right? Because this was geometrically trivial. Now this is already drawn. Right, because there is this random character, but if L tensor chi was the run, then L dual tensor chi dual was also the run, but now tensoring them together, this ambiguity disappears. So in that way you can make it.
Do you think the answer to that Liu-Zhu question is yes?
No, I'd be kind of surprised. No, I think, they're careful to raise the question, answer to which is certainly positive. I think there's a larger chance that if you start with a local system on a variety over a number field, then it should be true.
But what if, I mean, let's just try to have like, in principle, this stuff is like reasonably explicit in all this monitoring and everything, right? So, what's the instruction to actually just check? Let's say, yeah.
Sure. I mean, so you've got I mean, sections of this guy. They are they're secretly sections of this OB to run, which are kind of p-adic periods of your bundle, and then the connection acts on them in some way. Here,
I wanted to like just numerically, like, can I literally numerically check if the answer is yes? That was right to local system with, let's say, the monitor be living in, it's a number field, and it's also a number field, but the local system is not arithmetic.
sorry, it's not arithmetic.
Yeah, so I want to disprove it, right? So I want the L to be not arithmetic.
Sorry. There's only this to raise this question. You have to start with a local system on a variety of a p-adic field.
So maybe I'll discuss that. I have a thought.
Sure. I'd be curious. I think you can prove some things. You can prove that like the order of quasi-nilpotence of local monodromies is preserved, but maybe the abstraction that there is not a canonical map from left hand side to the right hand side. But no, you should definitely prove this. Yeah. So,
For sure, no.
Even more so, you should disprove it.
I have some different questions. So, like this type of like local system on some p-adic variety, like sometimes people say this is like the example family of Gauss permutations, like at each point you have Gauss permutation. So, is there some specific example if you take, for example, x equal to p1, and then like some local system, and then if you take like stock at each point, so like then choice of point is some kind of like a parameter, and can we like detect this parameter inside of this stock, right? As a Gauss representation, like what is the changing information inside of the representation?
Right. Well, so for P1 itself, it's accidentally a simply connected variety. The information would not be changing. But I get your question. You're saying we can take some more interesting base. Well, it's kind of the subject of, if you like, an abelian geometry. I mean, it's, for instance, this family of Legendre family of elliptic curves which came up. Oh, sorry. Let me backtrack. Let me just give you a different answer to this question. So there are versions of the period maps that Andy talked about. There are p-adic versions of that. So these are maps basically from your base variety to a certain space, which in a way is a moduli space of Galois representations. But sorry, maybe so there is when people say family of Galois representations, there are usually two meanings. One is in terms of Mazur's deformation theory, but that's not what we're doing here. Right. And so when I say moduli space of Galois representation, I mean some in the latter setting. So there are some maps to also similar. I mean, kind of, as you know, the Galois representations, say crystalline Galois representations, they're parameterized in terms of linear algebraic data, right? The filtration on a vector space in the Frobenius. And so you can see that such gadgets are parameterized by some flag variety, quotient by the action of Frobenius. So yeah, these things do have analogs of in the relative setting, if that's the kind of thing you're looking for. Or we can talk more detail after. We should probably thank all the speakers of all the talks.
And the organizers.
Oh yeah, well, the organizers. Thank you.
Thank you all for coming. Hope you had a fun week. Learned a lot.
Sasha, here's what I want to do.
Yes, please.
I want to start with a